Hello, everyone. As you may know, I made a mistake with the audio for the session that was live on YouTube. So we're going to have a recording from the office to describe what we talked about in class. So today we're going to first give a little recap on what we did last time in terms of static equilibrium, and then we'll move into talking about mechanical springs, the devices that are probably familiar to us, or most of us. And then we'll move into talking about bars and as springs and Hooke's law. Next, we'll treat superposition, and finally, indeterminate axial loading of bars. So briefly, the last time we met, we discussed methodologies for using static equilibrium to describe the external forces and the internal forces on bars, shafts, beams, and trusses. And the basic idea is that first we want to solve for the constraint forces or the reaction forces externally acting on one of these primary structures. And we want to use some type of coordinate system when we're doing that. And as we apply Newton's second law, both for forces and moments, we're able to calculate these external forces acting on the system. Then, if it's a bar, shaft, beam, or truss, we can use method of sections, where we apply Newton's second law. We discuss the orientation of the forces that might be coming out of the surfaces where we make cuts, and how we might apply Newton's second law in terms of summing forces and summing moments. With the bars, once you do an internal cut, it's a two-force member and you don't expect there to be any summation of moments. For the trusses, we can also use method of joints, and we apply Newton's second law. No summation of moments, but looking at the summation of forces at the joints and being able to solve for the internal forces in all the members of a truss. We also showed how we can use some linear algebra to solve for these systems of equations in IPython. Going to our new topic, first let's address mechanical springs. So springs are often coiled in nature, and when you take DMC or design mechanical components, you will get to discuss the role of the coil diameter, the wire diameter, the number of turns, the material in terms of the effective spring rate or spring constant or spring coefficient that you expect for these types of devices. Real structures, though, also behave like springs. So the bars, in particular, are what we're going to be focusing on today. And we haven't discussed how the material properties affect the elasticity or the stiffness of the bars yet. But we have kind of this previous understanding that we can assign spring constants or spring coefficients to mechanical springs, and we're going to assign them to bars today. Hooke's law, which you are probably familiar with, often appears in a couple of different forms. So F equals minus kx or F equals kx. Both are correct, and we use one or the other depending on the type of analysis that we're considering. So if we're thinking about the amount of force that we have to exert to pull or stretch a spring, F equals kx is an appropriate equation. If we're thinking about equations of motion where we're thinking about how the location of the mass changes and the forces acting on a mass, then F equals minus kx might be more appropriate. We also in the past have discussed, not in this class, but I'm sure you have discussed springs in parallel and springs in series. Just as a brief recap, not to do the derivations here, but springs in parallel add. Their spring coefficients add, I should say. And so if you're thinking about the effective spring constant, you're going to take K1, K2, you're going to add them to each other. And if there are more springs in parallel with each other, you would add them all up. Springs in series, they are going to add, but the inverse of the effective spring coefficient is going to be equal to the summation of the inverses of the individual spring constants. So in this case, what we see here are two springs in series, and you have K1 and K2. And so the 1 over the effective spring coefficient is going to be equal to 1 over K1 plus 1 over K2. Now, skipping the derivation here, but if you would like to look at the derivation, you can go to this nice YouTube video. The derivation, though, is based on the idea that the displacements for these springs in parallel have to be the same, but the forces can be different. Whereas in the series, or the springs in series, the displacements of these individual springs can be different, but the force in both of the springs, or in as many springs as you have in series, is going to be the same. So we've now discussed mechanical springs. Let's move on to thinking about bars as springs. And a bar under axial loading, okay, we put some forces on the top and bottom, is going to have some stretching or compression. And we can think about it changing its length by an amount delta. Now, like I mentioned previously, we're not going to describe, it's not a very hard equation actually, to describe the stiffness of a bar. But for now, we're just going to say, take it as a given. I'm handing you a bar and I'm handing you this spring constant for it, okay? So this bar has a diameter of 1 centimeter, a length of 10 centimeters, and the spring constant is 165 kilonewtons per millimeter. Just as we did in the first session, we're going to discuss the scaling rules or scaling relationships. So even though, you know, this number kind of came out of the ether, we can think about how this number might change when we change the length and we change the cross-sectional area. So if we double the length of the bar, okay, what do we think is going to happen? Well, here's what the bar looks like initially. It's got some length to it. It's got a spring coefficient. It can be drawn as a coil. And if we double the length of the bar, what is the new coefficient going to look like? Before we get to that number, though, we might think, well, look, I've got one bar here, and one bar, you know, and I've got another bar next to it. It's like putting two springs in series with each other. So we take this Ki, or the initial spring constant, and we put them in series with each other. And if we put them in series with each other, we can calculate what the effective spring coefficient is going to be. And so we do that here. And the result is that the spring coefficient is going to be half of what it used to be. And this is an interesting principle. So as we take a rubber band or a material or a bar and we put it side by side with another one and we attach them to each other, as we make that longer and longer, we have the opportunity to have more displacement for a given amount of applied force. And we can think of a scaling relationship as being take the new length, take the original length, and make a ratio of them against the initial coefficient, and that will give us the new spring constant. So in this case, we can say, hey, I'm going to take the initial length over the new length times the initial spring constant to get a new equivalent spring constant. So we doubled the length, right? So this, you know, since this is Li and this is 2Li, right, that's going to be 1/2 times the original spring constant to get us a new one. If we half the length of the bar, well, the opposite will occur, we're going to double the spring constant. Now, what happens if we double the cross-sectional area of the bar? Well, doubling the cross-sectional area is kind of like putting two of the bars right next to each other and, balancing them, balancing or putting mass on both of those two bars. And that's essentially, increasing the cross-sectional area is essentially, putting more of these things in parallel with each other. So if we do that, what we find is that we have these springs in parallel, and we're going to end up doubling the spring constant. So the general scaling rule there is that for a new area, an original area, we can come up with what the new spring constant might be. So let's do an example. It's pretty simple, straightforward. Spring with a mass. So if we have a mass, or a weight, better said, I guess, of 2,700 pounds, which is the same as 12 kilonewtons, and that's a force that's being applied to this bar we've been talking about with a stiffness of 165 kilonewtons per millimeter, how much will the bar extend? So what does this look like? Well, here's a Roadster. This is an old one, I guess, because I believe they're releasing a new model. And this mass is about what we're talking, or the weight is about what we're discussing here on Earth. Or you could think about a sedan, okay? And I'm definitely more likely to be driving one of these than these. And now we ask ourselves, what amount is the bar going to extend? Well, we have our force, we have our K, F equals K delta, right? Which means that we can solve for the displacement. And it's a little bit eye-opening, I think, to think about how much displacement we're getting. You might think, that bar, I'm envisioning like a bar, maybe 10 centimeters is this, and my pinky, 10 centimeters. So it's kind of like that, How much is that going to extend? It turns out, according to these calculations, about 0.073 millimeters. That is 73 microns, or 73 times 1 e to the minus 6, 1/1,000,000th of a meter. And that's not a whole lot. I mean, I guess it depends on what you're comparing to. If you're comparing to the nanoscale, okay, then it's a lot. But if you're thinking about what I can see without a microscope, it's about the width of a hair. So I can see that, and that's a pretty small amount. So kind of for your good to know file, the diameter of hair is about 75 microns. Sometimes I say 50, 100, whatever. It's in that ballpark. And here is an image from Wikimedia Commons showing a scanning electron microscopy image of a hair, and I kind of use my finger. I think this is probably around 100 microns or so. The little green bar there is supposed to be 10 microns. So this gives you a little bit of an idea. That bar is not extending a whole lot. Let's do another example. This one's more complicated. Now what we're saying is, we discussed how one spring will deform or extend under a given load. What if we have a network or a group of these springs? And we can apply our understanding for how springs add, or our inverses of them add, to describe their behavior in parallel or series, right? So first, this configuration has a K1, 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 all right? And we're assuming that these bars, the vertical bars, are deforming or extending, while the horizontal beams are rigid. And in this case, we're also going to say that these different parts of the system are symmetric, okay? So we don't have to worry about moments. So the force in this member is going to be the same as the force in this member, because they have the same coefficients of springiness, same spring constants, okay? And we're going to say that, things are symmetrically balanced here as well. So we're not dealing with moments. We will later, okay, deal with moments and how that can affect the equilibrium. And we're also going to say there's no rotation. So this member here, this beam here, and this beam here are not rotating. So how might we go about simplifying the description? Well, let's first make a diagram where we have our K1s and our K2s and our K3, or just, I guess, 3 K1s, 1 K2, 1 K3. All right, put them in a diagram that looks something like this. And you're like, this kind of looks like a circuit diagram. Yeah, well, with circuit diagrams, right, we can manipulate things. We can do resistors, capacitors, and series and parallel. We have those rules for the impedance, and we can kind of simplify the diagram. We're going to do the same thing here. We have K1, K1. These two guys are going to be in parallel. So we can just add them to each other, 2K1. And now we realize, well, this one is in series with this one. So we can add the 2K1 and the K1. Well, we're not add, they're in series, right? So we were going to do like 2K1 times K1 over 2K1 plus K1. This ends up being 2/3 K1. And then this leg is in parallel with this leg. So we can go, okay, first we have to write it out. So we've now put these guys in series, but this leg's in parallel with this leg. And then we can put these guys in parallel with each other, which means that they will add nicely. And then that's in series with this portion, this spring with spring constant of K3. And then write an effective equivalent spring constant, or write an effective spring constant as you see here. Okay. So this is pretty straightforward, using the rules that we've established for springs in parallel, springs in series, making some assumptions about how much rotation or not rotation we're having, how symmetric things, how rigid the beams, the horizontal beams that are connecting everything together might be as well. What does the deformation look like for this system? Well, let's pick some representative values for the coefficients of these springs. And this would be maybe a smallish system if it's height, or they could be really narrow or small diameter, or larger diameter, sorry, cross sections of bars, but they're longer. But let's just pick these values that you see here. We have K1 equals 200 kilonewtons per millimeter, K2 is 150 kilonewtons per millimeter, K3 is 100 kilonewtons per millimeter, right? The first example that we were doing, we said 165 kilonewtons per millimeter. And we'll apply a force of 1 kilonewton. With that amount of loading and running this script that was written in IPython, which you can download, we see that the displacement is only 13.5 microns. That's pretty small, right? We were just discussing how 75 microns is the width of a hair. So this displacement is calculable and may or may not affect functionality, but as we'll see later, there can still be significant forces associated internally with this structure. Another thing to look at is the equivalent spring constant. Now, yes, there are a couple of these legs that are in parallel with each other, so we would have an increase in the spring constant with springs in parallel, but given what we see with these elements in series, the resulting spring constant ends up being less than what we had originally. So when we're doing these calculations, it's not a bad idea to kind of check. say, oh, does this make sense? If I put a bunch of, if I stack these springs, like you see that's in series with that, which is in series with that, and I'm kind of making things longer, even though some things are in parallel, is it in the same ballpark for an overall effective spring constant? And it is, and it's less, okay? Significantly less. Let's now modify this example that we just discussed. Now we're on to example 3.3. And what we're going to say is rotation is now permissible in this lower beam. It's initially horizontal, but maybe it can rotate. Once again, we're interested in the displacement that we might have here at the end. And we're going to still assume that this beam and this beam are rigid. This one can rotate, but it's rigid. And we're going to still assume that these bars are deforming. Notice also that we've moved this bottom vertical beam a little bit over to the left. And so now we have A, B, and C as points describing the positions of where this bar connects with the beam, where this bar connects with the beam, and where this bar connects with the beam. And we can describe distances between, say, A and B as LAB, or distance between B and C as LBC, or distance between A and C as LAC. Using what we did before, where we said, okay, this is a symmetric system, we can come up with an effective spring constant for this region. We have 2/3 K1, and that's going to be the spring constant for what we're going to call our kind of leg one, all right, like we have here. This spring constant stays the same over here, and we'll have our K3, I didn't write it there, but this has got a spring constant of K3. Let's go ahead and take a look at equilibrium on this horizontal member, this horizontal beam that's completely rigid. Now, we're going to assume here that this member is flat. And you may think, oh, that's not a great assumption because you said it could rotate. Yes, it can rotate. But the rotation is going to be very, very small, as we'll see in a little bit. And thus, the change in the moments as the beam turns are going to be pretty insignificant. So we're going to say, for doing this first part with equilibrium, just keep it horizontal. Now, if we sum the forces in the y direction or in the vertical direction, we get the following, setting them equal to 0. And if we sum the moments about A, we have the following, where we have this F contributing a negative torque. It's going in to the page, right? If I use the right-hand rule. And if I look at the torque from F2, this isn't a positive, it's coming out at me. And now we have a nice relationship between F2, which is the force in this spring, and F. It's a ratio dependent on this length, LAB over LAC. And we can plug F2 back into this form, or this equation of equilibrium, and solve for F1, and we get that that's LBC over LAC times F. Note, if I move this big F closer and closer to this A, or closer and closer to the left side, that means LBC, this length here between B and C, is getting larger and larger. And that kind of makes intuitive sense then that this F1 on the left side is going to be handling more and more of that load. And F2 on this side is going to be handling less and less. This is not much different than thinking, oh, Archimedes is going to make a lever and be able to support a massive amount of weight with a little amount of force as the length of the lever becomes longer and longer. And of course, we're using a completely rigid beam. We're not worried about the beam bending or breaking at this point, so we can make a great lever as long as we want to support a huge load. But we digress. Now, let's copy what we've done here and start looking at what happens to this member as it rotates. Now, for this, what we're going to say is the change in length on this left side, on this left leg, we're going to say, for now, we're just going to assume that it's larger than the change in length on the right side. Okay? And we're then going to draw the horizontal beam followed by a rotated beam. Now, maybe I should have done A prime, B prime, C prime, but these are the same points. Maybe a slightly subtle but important point is that the beam displaces downward. Okay, you're like, I got that, right? So we can actually describe the displacement delta 2, right? How much the C goes down and how much delta 1 or how much A goes down with these parameters, delta 1 and delta 2. Now, delta 1 and delta 2, what are they related to? Well, they're related to how much this leg stretches and how much this leg stretches, which are, these stretches are related to the forces in them, right? We have some type of spring constant, we have some type of displacement, and we have force. So we can apply the F equals Kx or the F equals K delta to relate this force or the force in this leg to the displacement on the left side. Similarly, we can relate the force on the right side to the displacement with the spring constant. Okay? So we're still assuming just linear, okay, dropping. Yes, if you want to be really particular, you're like, yeah, well, you know, technically these springs are getting a little bit closer to each other. We're going to ignore that. Yeah, we're going to ignore that phenomenon. Now, how do we describe the angle of rotation? Well, I could draw angle relative to horizontal, you know, going through B, A, we're doing it through C, and it'll hopefully become obvious why that's not a bad choice here. And we'll say there's some theta there. What is that theta equal to? Well, we see we have a right triangle here, and we see that this opposite side, okay, from there to here, can be described as having a length of delta 1 minus delta 2. And we know the length of this hypotenuse, so why not say that the sine, the opposite over the hypotenuse, is delta 1 minus delta 2 over LAC. Now, other people may decide that I want to use this adjacent, what we're thinking is adjacent as LAC. So they would write tan theta equals delta 1 minus delta 2 over LAC. That's actually fine. For small angles, it's not going to make a difference. Small angle approximations for minus 10 degrees to 10 degrees will show you that sine theta and tan theta are essentially the same. They're very equal. And so you could pick either way to work this problem, but we're using sine theta here. Now, we can do some substitutions back into this formula, okay? But before we do that, maybe we want to write out what delta 1 is equal to. So we're rearranging terms here and putting in terms that describe F1 with respect to the force being applied at the bottom, and delta 2 similarly being rearranged to be in terms of F. And then we plug in delta 1 and delta 2. So delta 1 goes in there, delta 2 goes in there. And we have an expression for the sine of theta. So the amount of rotation essentially of that beam. And we already said we expect this rotation to be small, which means that we can also use a small angle approximation here and just drop the sine theta. Turns out it doesn't really matter, but it's, let's just say that we've now figured out the angle of rotation in terms of this force, the spring constants, and the lengths, the position of this bottom spring along the lower member. Copying, this is just copying what we just did and going a little bit further. We still haven't written an expression that describes the deformation delta. So let's look at the geometry once again, but maybe with a slightly different perspective. What we're going to do is now think about this delta 2, right? We already had this delta 2. This is how much this is extending on that side. I'm not writing delta 1 again, although delta 1 would be, this distance here from this the horizontal down to A, right? We did that on the previous slide. So delta 2, an angle, and we can describe the distance of B, right? How much this is dropped based on an LBC, right, times the sine of theta. That will give us this opposite side. Okay, so delta 3 is LBC sine theta. And so now you're like, oh, well, you told me to get rid of the sine. We could have kept the sine in because we're going to substitute this in here in a minute. Now, there's also some deformation of this bottom spring. Delta 4 is equal to F over K3. And if we add delta 2, delta 3, and delta 4 to each other, we will have an expression for the resulting delta, which we can write out as such. So we've accounted for rotation, accounted for translation, and now we have an expression for deformation. What type of deformation do we expect from this system, and how does it compare to the very similar network that we just described, where there was where rotation was not permissible? So let's plug in some values. These are the same values we just used with the previous example, except we're going to add in also a parameter for the distance between LAB and the length LAC. That will not be super obvious, I guess, but if you look in this code, what I did is I said it's 0.3 meters. Okay, so LAC is 1 meter, and then LAB is 0.3 meters. And if we run things again, looking at the code and running it, the displacement we get at the end is 14.3 microns. It's not that different than what we had the first time, where we had 13.5 microns. So you're like, what's the point? Well, we've gone through this exercise as more precise, is accounting for rotation. But yeah, if I'm just concerned about displacement, it's probably going to be pretty hard to distinguish the two of these systems from each other. But what happens if we change the parameters a little bit? What happens if we make this side more stretchy? In other words, we lower the coefficient over here. That means if this is more stretchy or this has a lower stiffness, right, we expect that the rotation will go up. And if we have more rotation, will that mean that it will have a more, the system will have a larger deformation than what we saw previously? So in this case, we'll change our K1 from 200 kilonewtons per millimeter to, that should be millimeter. That's not right. Sorry, guys. Sorry, everyone. And just like that. if we change the coefficients, or just the first coefficient actually, from 200 kilonewtons per millimeter to 20 kilonewtons per millimeter, what is the effect on the system? Well, we've lowered the spring constant here, which means that we expect more deformation even in the case where we're saying there's no rotation and the system is symmetric and there are no moments on the lower beam. So we went from 13.5 microns to 16 microns. Okay? And with this change, though, we see a very large difference in the deformation we expect when we consider rotation. Before, we said it was like 14 microns. Now we're up to 47. And we went from, it was still somewhere between 1 and 10% change here. I haven't done the exact numbers, right? But like 0.8 divided by 13.5 or something, it's something. It's something less than 10%. And here now we're talking a change of almost 3x, right? So a change of almost 300%. So as an engineer, we have an opportunity to think, oh, do I need to account for rotation? Do I not? And then use the appropriate assumptions to be able to model the problem appropriately for our needs. The next topic we're going to treat has to do with superposition. Now, superposition is something that you are familiar with since you've been adding things together for a long time. We've all been doing this. And a more formal definition of just adding things together is what you see here. And I like these words found on Wikipedia, yes, and it's distributed to the Penguin Dictionary of Physics. But it says the superposition principle, also known as superposition property, states that for all linear systems, the net response caused by two or more stimuli is the sum of the responses that would have been caused by each stimulus individually. So that if input A produces response X and input B produces response Y, then input A plus B produces response X plus Y. For axial loading, if we have F1 acting on a system and we have a delta 1, and we have F2 on a system and we get delta 2, then the addition of these, or if I put now F1 plus F2 on the system, then I get theta, or delta 1 plus delta 2. Notice they add to each other, and this is a linear system, right? So, it scales linearly as I increase the force. In a real system, it will be linear to a point, right? But as I introduce more and more mass or weight, and I increase the load to get to a situation where the bar is going to want to plastically deform, then as I add a little bit more force, I'm not going to get the same linear I'm not going to get the linear response. It's not going to obey the rule of superposition. So that's an example of where you want to be operating in the linear regime to be able to apply superposition effectively. Let's do an example. Here we have an axially loaded bar that has 3 sections. And the first section has force 1 acting on an F1. The second section on this side of it has F2 acting in the opposite direction. And then F3 is acting over here. And we want to know the overall displacement of the system. We don't really need the lengths. I wrote them here, and that's fine. We don't really need them because they gave us, or I gave us K1, K2, and K3. What we are going to do is use superposition to calculate this overall displacement. And how do you think we're going to do that? Well, we said that a response is equal to the summation of the responses of the individual inputs. That's what superposition allows us to do. So now what we'll do is take the entire system, and look at how it responds just to the F1. Look at how it responds to just the F2, and look how it responds to just the F3. Look at those corresponding individual displacements and then add them up to each other to get the overall displacement for the system. And in addition to being kind of this superposition principle being revealed, we'll also have an opportunity to review what we understand about the internal forces in these sections of an axially loaded bar. So, for example, let's look at this section here on the left section. I didn't draw the reaction force F1, the external reaction force, but there does need to be an external reaction force on this left side. And that's going to be equal, of course, to F1. So that's what you see here. If I take a slice, whoop, right down there, what I'm going to see is an internal force F1 as well in that slice. Now, it may look like that F1 is contributing to forces in the rest of the members on the beam, but there's no constraint on this side, and there's no force. I mean, there is in reality, okay, but for this individual case with just F1 acting on it as part of, superposing up to the system with all its forces, we have no force acting there. So there's no force acting there. So if I think, okay, what's acting here is 0, then I take a slice here, okay, I also have 0. And then similarly, there's no force acting on this individual inside member, okay, all right, because there's no action-reaction pair. So this action-reaction pair is 0 if you want. Then I take a slice, that's going to be 0 here as well. So this orange and this purple region are essentially just along for the ride. There's no tensile or compressive forces in them. They do displace, but the displacement is due to the internal force in this member on the left. This is kind of an important and subtle point. The cut I take here or here or here, they're all the same in terms of the internal force. And so what we need to do is figure out what is the stretch, right? What's the extension of that left member of this system to figure out what is delta 1. And F equals K delta. So delta 1 is just going to be F1 over K1. Now, let's take a look at the contribution of F2 to the beam. So we don't write F1, we just write F2 acting here. And we're going to look at the resulting deformation, delta 2. Excuse me. So where do we start? Well, there has to be a reaction force on the left side again. And its F2 is going to go all the way through this structure if we do external equilibrium. And so why don't we start with the left side again, and there's the reaction force F2, and if I take a slice here, the internal force is going to be F2 as well. Moving into the next section, if I were to take a slice, okay, here, I know that I have F2 acting on this side, and so internally I had to have F2 acting on this side to keep it in equilibrium. And if we go to the right now, what we see is that there's no force acting on this side, which means that there's going to be no force acting internally on this purple member either. K1, K2, these are the relevant stiffnesses for these members, and the force F2 is acting through both of these members. Now, which direction is this force acting? It's acting opposite the direction of delta 2 here, and it's acting to put these two members in compression. So if we figure out the effective spring constant of these two members, which two springs in series, we've done this now a few times, K effective is K1, K2 over K1 plus K2, then we can say that we can calculate out what the resulting deformation is going to be here. Okay, so delta 2 is equal to minus F2 times quantity K1 plus K2 over K1, K2, as you see here. Now, another way to think about this system is to say, hey, I'm going to look at the elongation or the compression of the individual entities. So I'm going to look at what's happening in the green one. I'm going to look at what's happening in the orange one. And let's just define these delta 2a and delta 2b. Now, these are in compression, so I'm kind of expecting that these will go negative. And I'm also thinking, well, delta 2a plus delta 2b is going to give me my delta 2, right? So like how much this extends or compresses plus how much this extends or compresses is going to be the overall deformation, right? And if you go back to the derivation that you would use for springs in series, you can look at it that way. You can say, hey, the resulting deformation of the entire network of springs in series is going to be equal to the individual stretch of the individual springs. So, or the summation of the individual stretches. I'm not sure if I said that. So now, another way it gives you exactly the same result is to say, all right, I know what the compressive forces in each of these members are, and I know what these deformations are, so I can add them to each other. And the individual ones are minus F2 over K1 and minus F2 over K2. And so they add as you see here. Next, we have a system where we apply F3 on the end. And we're going to look at F3 and we're going to look at delta 3 there. Now, this one may be the simplest one. You're like, oh, it's just 3 springs in series. And you're right. Okay, and you don't have to think about the reaction forces, you don't have to think internal forces, just give me the effective spring constant and we're good. But just for kicks and also further clarification, right, what we're going to do is break down these individual members. There's a reaction force here on this side, okay, that is going to be acting on the left side of this green portion, and the internal force is going to be the same, F3. When we take a cut here, okay, we're going to have F3 acting against the green side, and or it's actually it's going to be it's going to be in tension. It's going to be so that that middle section is still going to be pulled apart, and the internal force is still going to be F3. And similarly, if we take a cut here, we have F3 acting on it, pulling it apart, and so that's going to be also in tension. So all 3 have the same force going through them, which is what happens with springs in series anyway. So if we want to write out the equivalent spring constant, it's 1 over KQ, right, equals 1 over K1 plus 1 over K2 plus 1 over K3. And we see that we have now a delta 3. So if we want to write the overall deformation, it's going to be delta 1 plus delta 2 plus delta 3, as you see here. Now, these treatments are very powerful because it would have been kind of trickier, I think, to try to go through. Maybe not. I mean, so I guess I should have done that, or could have done that, but we don't want to make things too long. Is I could have said, hey, I'm going to think about delta 1, delta 2, delta 3 as being the elongation or the compression of each of these individual members. And if I go about and I do my cuts, right, I can figure out what the internal forces are in each of these members, and thus I can, with that internal force in each member, I can figure out what the displacement is, right? So that's a possibility, and I guess I'm going a little bit off script here, but for example, the reaction force here on the wall with all 3 of these, right, that's going to be F3 plus F1 minus F2, right? That's the reaction force there. And if I took a cut there, that would then mean that, okay, that's the internal force. I can figure out how much elongation I have from the summation of these external loads. Okay, that's the internal force based on the external loads. And so I can figure out what the elongation of that member is. And I could do that for that one, and then this one, and then this one. So that's another way to look at doing this problem, if you will. But we did it using superposition instead. Okay, let's put in some numbers. So if we use 200 kilonewtons per millimeter, 150 kilonewtons per millimeter, 100 kilonewtons per millimeter, and we have F1, F2, F3, as you see here, then we can calculate out what the overall displacement is. And it's about 32 micrometers. Okay, again, not a tremendous amount given the numbers that we're using here, but calculable and an example of using superposition. Now, the last topic we're going to address today with indeterminate axial loading on bars is going to demonstrate that even though there may be very small deformations involved, the stiffnesses of these systems and their configuration can lead to uneven or highly variable distributions of forces within the structure. And hopefully that statement will become a little bit clearer in a few minutes as we discuss determinate and indeterminate axial loading. In determinate systems, we've become comfortable in solving simply for the reaction and internal forces. In other words, this is statics. This is what we've been doing. Put the force on the structure, solve the external equilibrium problem, then dive in, find out what's happening internally in the structure. And when we look at a system such as this one, where we have one force acting on it, and we have a reaction force of the wall acting on this member here, what we see is that the internal force is just equal to the reaction force here. And if we took another cut here and we're going from the left, we see now that we have no force in this side. We've been able to solve for the reaction force F at the wall and also the internal forces without thinking at all about displacements. We have essentially one equation per variable. Okay, so if you have one equation with one unknown, if we call this Fi instead of F, for example, then we need to figure out something, right? So, with respect to, one equation, one unknown means that we can solve for the unknown, essentially, right? An indeterminate system is when there are more unknown reaction forces than non-trivial equilibrium equations. Okay, a structure is statically indeterminate. So I like this description from ECU SW. What is this saying? This is saying that, look, we may have more unknowns than we have equations. And often it's like, oh, I have two unknowns in my force equilibrium. Let me look at the moment. That will give me one more equation. So then I'll have two equations, two equilibrium equations, and two unknowns. Boom, I can solve for both of them. And I'm done. But if it's a statically indeterminate system, we exhaust what we understand with equilibrium. And we still have an imbalance. We still have more unknowns, more unknown variables than we do have equations. So we would like to be able to find another equation somehow. And that's where we use compatibility equations. All right, what are compatibility equations? Well, compatibility equations involve displacements. And the displacements must be compatible with the problem geometry. Well, we've just been talking about displacements, right? We've been discussing how forces and displacements are related to each other with stiffness. So let's do a modified version of the problem that we drew previously. Same bar-like structure, but now we've added a constraint on the right side. And you're like, it's not a big deal. Well, it adds another reaction force. We have two sections, the external force acting on it, still have this reaction force on the left, but now we have a reaction force on the right-hand side as well. So if we sum the forces in the x direction, what we have are f minus r1 minus r2 is equal to 0. Okay? Just like that. And those are two unknowns in one equation. What do? Well, you're like, oh, it would be nice if we had another equilibrium equation. But we can't apply moment equilibrium here because it's an axial one-dimensional problem. So we're kind of stuck. And thus we see this is an indeterminate system. Now, we apply what we know with indeterminate axial loading, okay, to be able to think about the displacements and how they can help us solve for this problem. So here we had one equation and two unknowns, R1 and R2. And we still have this system, but let's spend a few seconds talking about the displacement. So we can say that we have our displacement of this side against this side, A. And the nomenclature that we'll introduce here is delta C slash A, which means the displacement of C relative to A. Now, this can be a little bit confusing, okay, because it's like, hey, which direction do I draw the coordinate system? Often, okay, you end up drawing some type of, positive arrow coming out of a surface. And so if we think about delta C A, we'll think about, okay, well, if C moves to the right versus A, right, that would be, a positive relative displacement. If this is in compression, right, and C and A get closer to each other, that would be, negative. So this is a relative distance, right? So, I mean, if you're going to get similar results if you think about, A moving relative to C, okay? But we're saying displacement C relative to A. Now, we can also describe the displacement of C moving relative to B, and we can also describe displacement of B moving relative to A, all right? And so this equation that we have here is summing these two individual displacements up, relative displacements up with each other to make it equal to the overall displacement. So we have displacement of C relative to B plus the displacement of B relative to A. It's going to equal, okay, displacement of C relative to A. What are we going to do with this? Well, we're going to remember that there are two walls, right, on either side of this system, which means that the relative displacement of C to A is just going to be equal to 0. Okay? And then we have to look at, well, if I know this is equal to 0, what are the relative displacements of these entities? Of the displacement of C relative to B and displacement of B relative to A. How do we think about this? Well, displacement and springs, they go together. And if I know what's happening with the internal force in a member, I can figure out how much it's extending or contracting, right? So now if I have R2 acting on the right side and I have an R2, internally on this system, and this is the right side and this is the cut over around here, we can say, hey, there's going to be a certain amount of displacement, okay, associated with this force. And it's going to be in compression and it's going to be negative. So the displacement of C relative to B is going to be minus R2 over K2. What about displacement of B relative to A? Well, as you can guess, you're going to have R1 internally, and that means that we're going to have a displacement of B relative to A. This is in tension, this was in compression, so it's going to be positive R1 over K1. Copying things over and going further, let's now plug these relationships into our geometric compatibility equation, which said that this right side is going to be equal to 0. And we have that minus R2 over K2 plus R1 over K1 is going to be equal to 0. And then we now have a relationship between R2 and R1. We had already a relationship between R1 and R2. So we've got two equations and two unknowns now, all right? Instead of one equation and two unknowns. We will be able to solve for the internal forces. So going in and substituting R2 into the equilibrium equation, we get this expression for F and R, and we can solve for R1. And going in and looking at the equilibrium, again, with R1, right, plugging this in, we can solve for R2. And we get, you can plug in R1 up here if you like. Okay, so you could do it either way. Okay, but we get that the R1 internal force is equal to the K1 over K1 plus K2 times F, and the R2 internal force is equal to K2 over this quantity K1 plus K2 times F. Now, this is one of the reasons why I like talking about the stiffness of bars without introducing the material properties. I mean, yes, K is a material property, but in some respects, as a bulk parameter, it's kind of abstracted out a level. Look at what happens to R1 if K1 is large. If K1 is big and K2 is small, then R1 approaches F. This means that if you have a very stiff left side here and a very stretchy or soft right side, that's not really the right word, I guess, but let's say stiff, less stiff, means that this side is going to have a higher force embedded inside of it than the right side will be. This is a very interesting and powerful concept, thinking in terms of stiffnesses. Often we think, stiff is stronger, right? And yeah, I mean, as something that's stiffer has generally more cross-sectional area for a given material. And so, yes, that could be true, but it could also be supporting a higher force. So let's look at another way of attacking this problem. This time, we're going to attack it with superposition. So before, we were using geometric compatibility and using our relationships between, for a spring to be able to solve that equation with two unknowns, to have two equations with two unknowns. This case, we're still going to think about springs, but we're going to think about the problem differently. What we're going to do is say, get rid of the constraint on the right side. Just let it go. Apply the force, and let's think about what the displacement is without this constraint. You're like, okay, that's kind of funny. So we have a force here, we have K1. We know that this portion is just along for the ride, but this portion here, it's going to be F over K1. That's what's being stretched to the right. Now, what happens if I want to enforce the fact that there's a wall here? That means, right, that the change in position of this right side of the beam has to be 0. And that means that there has to be some wall force, right? The same wall force before that we calculated in the other case needs to be applied to get this to go back to 0. So we'll call this FR, okay? Although this FR is, in the end, the same as R2, okay, that you have over here. Let's just call FR. I'm applying this restoring force. And when we do this, we say, okay, this delta 1 that I have and this delta R, okay, they have to be equal to each other, or delta 1 minus delta R has to be equal to 0. This means that we have delta 1. Well, okay, so this is the power. This is where, our geometric compatibility comes in. And then we can start to think about, okay, what is delta 1? What is delta R? Delta 1, we discussed previously a second ago, is just F over K1. Delta R, right, is going to be this restoring force times these two, the spring constant associated with these two members in series with each other. So now I can calculate out delta R. We put them together, we equate them, and geometric compatibility. So now we have, equations that are describing the displacements in terms of the forces. We put them together, we get F minus FR times this quantity, and we do a little bit of algebra, and we figure out that FR is equal to K2 over K1 plus K2 times F. This is identical to what we said for R2 in the previous problem when we had it going there. And if we look at R1, okay, using external equilibrium here, so we have R1 and FR here, and we have F. We can write out what R1 will be, and as you can imagine, it comes out to what we got last time as well, where it was K1 over K1 plus K2. So we get the same results as using geometric compatibility, and some would say that this approach is simpler, okay, using superposition, releasing a constraint and then applying a force or applying a load to get back to geometric compatibility with what the initial constraints were offering. Now let's look at some values. If we say, okay, K1 is 200 kilonewtons per millimeter, K2 is 100 newtons per, or 100 kilonewtons per millimeter, and that the load is 1 kilonewton, we can run the numbers as we've seen here, and we get that R1, okay, so this force on this side, this internal force also in this member here, is going to be 2/3 of the force that we're applying to the system, and then this side is going to be 1/3 of the force applying to the system. How interesting, right? Double the stiffness, 2/3 of the force. Half the stiffness, 1/3 of the force. We've used geometric compatibility, we've used superposition to allow us to solve a problem that was not solvable just with using equilibrium. One other interesting point is that the displacement, okay, that we have here, if we say, hey, tell me what is this displacement of just F over K1, right? Now, this F over K1, this was the unconstrained displacement, okay? The F over K1. That was only 5 microns. Okay, that was only 5 microns. And or I should have probably calculated it if you have these two things together, going back to the original problem. This is the unconstrained problem, but it's going to be even less than that, okay? And actually, it should, if I'm not mistaken, it should be 1/3. No, it should be, so, okay, it should be, yeah, it would be 300, a spring constant of 300, so it would be essentially 2/3, okay, of what it would be otherwise. So like, something less than 5 going this direction. That displacement is very small, 5 microns. We talked about displacements, but nonetheless, the distribution of forces in the system is significantly different, even though there's a small amount of deformation involved. And that is something that I think we can appreciate as an interesting result that accounts for stiffnesses, okay, different stiffnesses, being able to have very large control over the distribution of internal forces, but yet we don't see these changes as being very significant in terms of displacement. Well, to conclude what we've discussed today, we've had a brief review of static equilibrium. We've discussed mechanical springs. We've discussed bars as springs. We have discussed superposition, and we discussed indeterminate axial loading in bars. So we've discussed quite a bit. Hopefully, the ideas of using methods of sections or method of sections and the relationships for springs are now more clear and allow us to be able to solve more problems, specifically the indeterminate ones that aren't solvable just using static equilibrium. If you have any questions, please feel free to send me a message, and I'll see you in the next session. Thank you very much for your time.